Well, let me just first thank the organizers for having me here. It's a great pleasure to be here. First time in the CIRM, so I'm discovering this fantastic place. I did not know the format or the audience, and so but the advantage of a Blackboard talk is that one can improvise and adjust to the audience's interests, and in particular also what people know, right? So, and I assume that this being a mathematics center, in fact, I was shocked that slides were allowed. So let me just to check to get a sense of where people come from. So who comes from mathematics? Who would primarily define themselves? Okay, so the vast majority. Computer science? Okay, all right. So I'm going to talk about various objects, but I just want to get a sense of what people have heard of. So I guess I can start, right? So I'm going to talk about monadic second-order logic, and also about Presburger arithmetic. And in connection with these things, about automata, which indeed is the A in Kant. So let's start with MSO, monadic second-order logic. Who is somewhat familiar with MSO? Okay, maybe like half. Who has never heard of MSO? Okay. What about Presburger arithmetic? People are familiar with it, and who has never heard? Okay. And automata. Who has heard of automata? Okay, okay, so you're all familiar with automata. Okay, good. Perfect. So let's get started then. So I want to talk about decidability question. Yeah, one more, sorry, and I'll stop after that, I promise. Decidability, who is familiar with notion of decidability? Okay, we're all very good. So if I, for instance, suppose I give you a matrix with, let's say an m by, well, let's just make things easy. Let's take an m by m matrix, and then I've got an m by 1 vector, and then I have ax, let's say, is equal to b, where x here, sorry, this seems to go a little bit, stop, okay. Where x here is a vector of variables, and suppose that I want, I ask, does there exist a solution for x in, let's say, non-negative integers. So here I would be in n. So I'm trying to solve this equation. So decidability of this means of this question means that there exists an algorithm to do this. So the people obviously know that this is decidable. Would people know how to if you're put in a small room and you're not allowed to, would people know offhand how one might solve this? Yeah. Okay, so you could solve it over the reals. So how do you know you can solve it over the reals?
Or even over the rational, solve it without the positivity condition.
Without the positivity condition. Okay. So I guess you could do this. So here, notice that I'm not assuming, one answer that I thought people were going to say is just multiply everything by A inverse. And then you get the solution, but you don't assume that A is full rank, right? So, yeah?
Maybe you can say this in Presburger arithmetic.
Ah, okay, very good. You can say it in Presburger arithmetic, invoke decidability. Absolutely. Yeah, so there are various ways you can do it, but you're right that solving it over the reals and then using, there are various techniques, kind of cutting plane techniques and whatnot that you can use to efficiently solve this. there's also a principled technique. There's these bounds that go back to the 70s by Borosh and Trebig that tell you that if there is a solution to this equation in integers, there is one where all the variables are bounded above by a certain constant, which is exponential in A and B, and it's obtained by forming the matrix A, adjoining the vector B, and looking at all minors. And essentially, it's a linear, and looking at the determinants of these minors and the maximum possible value of these. And it's a linear function of these minors, and that gives you an upper bound on X. So that gives you, in principle, a way to search for solutions. Okay, so does that make sense? But it's kind of, I'm just trying to illustrate that indeed it is not trivial, and you can do this in Pressburg arithmetic, and Pressburg arithmetic is in fact more powerful than this, and it kind of tells you that the decidability of Pressburg arithmetic is perhaps not something completely obvious. Just one last thing in this vein. Suppose here I give you, instead I give you polynomial equation. So here you have a linear equation. So I give you a polynomial with variables, let's say, here I've got n variables. So I've got a polynomial with these n variables, and I'm asking, does there exist x1 up to xn in n such that I guess let me just write just so we. Does there exist values such that natural number values such that I have a 0? So now, would this be decidable? No? Who said no? Yeah, why? Yes, very good. It's Hilbert's 10th problem, exactly. So, so that has no, it's undecidable. Hilbert proved this. Interestingly, I was discussing this question with a number theorist not very long ago, and this person told me, oh, they never really understood this Hilbert's 10th problem. I was a bit shocked, and so we started discussing. And it turns out, I said, well, what does it mean that there's an algorithm? And I was a bit shocked, and then I sort of explained. I said, well, it means that you cannot write down the Turing machine such that you would put down so on and so forth. Ah, it has a Turing machine that has a mathematical definition. And I said, well, yeah, of course. Ah, so all of a sudden. But the reason I'm bringing up this anecdote is that some number theorists don't think about decidability question. They think of effective, bounds, and which are all very closely related, but they don't necessarily think of this idea of something being decidable or not. And there is, of course, this unfortunate terminology clash whereby we refer to the undecidability of the continuum hypothesis when really it's an independence. It's independent of the axioms of Zermelo-Fraenkel set theory. So it's a different notion of undecidability, which sometimes mathematicians are more familiar with. Okay, so just another, suppose instead I ask, let me call them maybe S and S1 now I ask them to be in R such that P of S1 Sn equals 0. Now, can that be solved? Yes, I see people nodding, yeah. So this is the decidability of the existential theory of the reals here. So in fact, the full first-order theory of real arithmetic is decidable. So so here, what I've said is, if you take the first-order theory over the natural numbers with let's say 0, 1 plus times, and you take also the first-order theory now over the reals and 0 less and times, then the first one is undecidable, and the second one is decidable. Okay, so This is a special case. The second statement here is a special case of the second statement there because it's an existential statement. The first statement here is a strengthening of whatever written on the top because already the existential fragment is undecidable. Okay, so far so good. So let me, let's see, how am I gonna, I'm not used to lecturing on the board, so I don't, my board management is quite rusty, I'm afraid. Let's go to, let's look at some simpler logic, some logic with fewer symbols anyway. So let's look first of all at Pressburg arithmetic. So Pressburg arithmetic, and this is a logic that was introduced in 1929 when, by the way, this undecidability result at the time was not known. And Hilbert had this program to axiomatize all of mathematics and also to be able to decide statements that are given in a logical formalism such as this one. This was the famous Entscheidungsproblem. And in 1929, of course, it was not known to be undecidable. That came later. I'm not going to say Gödel, although you can get it from Gödel's theorem, but that was really Turing and Church, sort of maybe a few years later, that I guess showed the undecidability. And the point about undecidability is that you need a definition of as we just discussed, of a notion of algorithm. That was introduced by Turing. But Tarski, at the time, was very much trying to prosecute this program. He had shown decidability over the reals of the full arithmetic. And so he asked his student Pressburger, well, let's try to decide this, but without multiplication. So usually we also include, let's say, order, and we may look at this over natural numbers or the integers, positive and negative integers. But the most important thing is we do not have multiplication. So this was shown to be decidable in 1929 by Pressburger. And the way in which he established decidability was through quantifier elimination. Now, we heard in one of the previous talks, in the first talk, Clement sort of started talking about these automata that read numbers in a particular base. And there is an alternate proof of decidability of Pressburg arithmetic that goes via automata. And then I will describe one such proof later on. In fact, I will embed Pressburg arithmetic into MSO, and by decidability of MSO, we will obtain decidability of Pressburger. Yeah?
Just a question about, so what do you mean that first order theory is decidable? Does it mean that for every valid sentence in the first order language, so for all languages, and
yes.
there's an algorithm that decides if yes or no this sentence is true in the theory or not?
Correct. Yes, I should perhaps have I guess almost everybody lifted a hand when they heard about decidability, but that's exactly right.
But first order theory, no.
Okay. First order, yeah, okay. First order is going to be important because MSO is S here stands for second order. So we'll come to that in a second. Yeah, so here, what kind of statements, I'll give an example of the kind of statements we can have, but yes, so what we just heard now is, first of all, you said valid. I think the word we should really use here is true, because validity talks about truth in every model. And here the model is completely fixed. This is natural numbers. Okay, so the model is completely fixed. This is natural numbers that we know and love, and no non-standard model. And now if I write down a formula using quantifying only over the first order objects. The first order objects are the members of n. So only quantifier over integers. I write down a formula that has no free variables. It's either true or false. Okay, for all x there exists y such that, something or other. It's either true or false. And decidability means there's an algorithm that will tell me yes, it's true, or no, it's false. It's always correct, always terminates. Okay, that's what we're talking about. Okay. let's see. So that was shown decidable in 1929. Let me just look at a slight. Now I want to look at expansions. So some expansions. So what's an expansion? So there's no sort of extension and expansion. Extension refers to when the domain is extended. So you start extending the domain, looking over a larger domain. So for instance, if you're over the rationals and you look over the reals. Expansions means that you keep the same domain, you keep the same signature, but you actually enrich the signature. So you allow more operators. So let's look at some expansions of Pressburg arithmetic. So for instance, we can look at Pressburg arithmetic with 0. So here, so I write first order 0, 1, plus, less than. And here I'm going to write SQ, and that stands for perfect squares. Okay, so I've added a predicate here, and this predicate says that it's a one-argument it's a one-argument predicate. So SQ of x says that x is a perfect square. So that means that it belongs to 0, 1, 4, 9, 16, 25, etc. Okay? Does that make sense? So now I can look at this theory, and I can ask, is this theory decidable? Okay, so it's a kind of natural it's kind of natural generalization of looking at this is decidable, and then you start giving your theory a little bit more power. Okay, does this make sense? So any thoughts on this? Have people seen this before? Yeah, okay, some of you have seen this before. Not too many. Okay, this is good. Any thoughts on so you can say something's a perfect square. Yeah.
For any subset that you can compute using your theory, checking if you in that subset will be decidable.
Yes.
So it's equivalent to asking, can you compute with 0, 1 plus whether a number is
not necessarily. No, I wouldn't say it's equivalent, because here you cannot. You can provably show that this set is not definable in Pressburg arithmetic, and the reason you can show this is that the only definable sets in Pressburg arithmetic are the ones that are ultimately periodic, and this is plainly not ultimately periodic, so it cannot be defined. So this is generally stronger, but nevertheless, it is conceivable that it could be decidable. Okay, so so just as any thoughts on decidability of this?
You could be ultimately periodic, but still up to a certain bound, because you've got the inequality. You could up to a certain bound, 100 squared, and then be ultimately periodic.
Yeah, absolutely. You can have any finite prefix in Pressburg arithmetic, of course, and but then eventually you must be. But this predicate square here is this. It's a predicate, or equivalently you can view it as a set, the set of perfect squares, and then you belong to the set. Rather than saying SQ of x, you can say, x belongs to SQ. That's the interpretation of this as a set. That set, the infinite completion of that set, is not ultimately periodic. So it cannot be defined in first order in just the pure Pressburg arithmetic. Okay, so let me just quickly show you this is actually undecidable, and the reason is that using the square predicate you can define multiplication, and I'm just going to sketch this proof here. How does this work? So the first of all, the idea is that if you have consecutive squares. Okay, so consecutive squares like 16 and 25, or 9 and 16. So consecutive squares. So they're of the form n squared and n plus 1 square, right? So consecutive squares. Now, of course, this is n squared I should say n plus 1 square. Sorry, n square and n plus 1 square. Yeah? So that here is equal to n squared plus 2n plus 1. So let me call this, because it's a perfect square, I'm going to call this Sn, and I'm going to call this Sn plus 1. So that's the nth square, and that's the n plus first square. Okay. So so now what we have is that if I take Sn plus 1 minus Sn minus 1 divided by 2, then that's equal to n. Now, I don't have division in my logic, but I can import division, because if I want to say that x is equal to y over division, sorry, by constant. If I want to say that x is equal to y over a, then I simply say that there exists an x such that a times x is equal to y, and the x in question has to be y divided by a. I can do this for any constant, because with plus, a is a fixed constant. With plus, of course, a times x is just x plus x plus x, a times, right? Okay, so I can do this. I know this is an even number, and then I can do this. So what have I done? I've said that if I have consecutive squares, I know I can know which element the first one is a square of. So essentially I have a square root operation. Okay, so why do I have a square root operation? Because if I know that u is a square, and I want to know what is it a square of, then I say, okay, well, I need to get the next square. So I have a for all, and I say, there's a number that's bigger than u, let's call it v, and between u and v there are no squares. And then v is a square. So u is a square, v is a square, there are no squares between them. I do this little operation, and I obtain a result, and that is going to be square root of u. Okay, does that make sense? Okay, so once I have this square root operation, then I'm almost there, because if I look at so I've got two numbers x and y, and I want to be able to have a formula that corresponds to x times y. Once I've done this, I have undecidability. So how do I do this? I use the fact that x plus y square is equal to x squared plus 2xy plus y squared. Okay, so I have x, I have y. Okay, then I can say, well, there's a u such that the square root of u is equal to x plus y. So I have x plus y squared. I got my hand on x plus y squared, okay, because I have square root. I've got my hand on x squared, because I say there's a square such that the square root is x. So the square, let's say I call it v. There's a v such that the square root of v is x. So I've got my hand on this. I've got my hand on that. And so that u is x plus y squared. That v is this. That w is that. And now, in order to get the 2xy, I simply do u minus v minus w divided by 2, and that's going to be equal to xy. So you can see how I can manipulate formulas, and finally I get multiplication. Yeah?
So maybe you can factor the argument in two parts. So you say that from a predicate or squares, you can construct a relation for being the square of something, and then you square
Yes.
some and take
Yes.
the square root into
Yes. Yeah.
So on the left you have the first one,
Yeah.
on the right you have the...
I think there are many ways to present this better than I did here. I completely agree. Yeah. No, you're right. Well, I'm saying better. I'm trying to give an informal sort of conveying informally without writing it down. But this is the idea. So okay. So does that make sense? So yeah.
The argument about explanation about importing division.
Yes. So suppose that I have a number. So suppose I have a number u, and I know u is divisible by 3. Okay. Suppose I happen to know this. I happen to know that u is divisible by 3, because it's been obtained through some calculation, and it has to be divisible by 3. But I would like to know what is u divided by 3. Okay? So then what I can do is I can say, well, there's an x such that 3 times x is equal to u. And now I do here whatever I want with the x. The point being is that now x is u divided by 3. So I've quantified, I've invoked a new variable, and I said 3 times this variable is u. Okay? And moreover, and now I've got a formula in which I use x freely. X is now u divided by 3. We do not have multiplication by, I cannot write x times y. But I'm, exactly. This is a constant. This is by a constant, not by a variable. Very important. Yeah, it's a very, very good point, very important. This is why I wrote a here, or maybe I erased it. So somebody said a times x is x plus x, but 8 times. But it's a constant. So here notice it's a bona fide constant, it's 2. Okay? Okay. By the way, this is very good. Just keep interrupting because this really helps clarifying things. Okay, so maybe this one is high enough, and now I tried with board number 2. Okay, I had these expansions, so I'm just going to write them back here. So I had these expansions, and the first ones, these are expansions of Pressburg arithmetic. So I had FO of n with 0, 1, plus, less than, and a square predicate. And that we've just seen is undecidable. And now let's look at FO of n with, well, actually, let me just continue on this before I go to another expansion. Okay, so we're happy that this is undecidable. Now, in the proof of undecidability, there was a crucial step in order to extract the square root, where I said that u is a square. At some point, I have that u is a square, and I know that u is a square. And I want to extract the square root of u. And how did I do this? Well, I said that v is a square. Okay, v is bigger than u. So I say that, so I'm existentially quantifying. I'm saying there exists a v such that v is a square, v is bigger than u, and moreover, between u and v, there is no square. Okay? So that requires saying that, so v is a square, and v is bigger than u, and now for all z such that u is less than z is less than v, I have that z is not a square. Okay. Why is this thing important? This thing is important because I want u and v to be consecutive squares. Everything rested on that. If u and v are not consecutive squares, I don't quite know what happens, right? So this requires a for-all quantifier, right? Because I have to go in between. So this led Büchi to ask the following question. What about the existential fragment of first-order logic of Pressburg arithmetic, with a squaring predicate? So I only allowed to write exist x, y, z, and then something that's quantifier free, essentially. Okay? Does that make sense? So well, so technically speaking, it's still open, although there's a paper as yet currently undergoing refereeing process by one Stanley Zhao that purports to solve a conjecture that Büchi formulated 50 years ago that would imply undecidability. So let me quickly explain this. So I'm not entirely sure whether the paper is correct. I think it may well be correct. But this has been open for 50 years. This paper is currently being reviewed, and it's a complicated paper. So what is so Büchi conjectured this was undecidable in 69, and he had a very specific conjecture that would entail this. So the Büchi conjecture, let's write the Büchi conjecture. So the Büchi conjecture was the following. So let S1, S2 up to Sm be a sequence of increasing squares, so perfect squares. So then he conjectured that there is some value of m. So m, I guess, is unspecified. But Büchi conjectured there is some value of m, okay, such that if the second difference of the sequence is a constant equal to 2, so let me write it this way. If the second difference of the SIs is equal to 2, then the SIs are all necessarily perfect squares, or consecutive squares. Consecutive. Okay. So so let me just say it again. Perhaps I should have put this. There exists an m. So his conjecture was that there's some value of m, some integer m, such that if you take any sequence of perfect squares, S1, S2, all the way up to Sm, they're squares. They're perfect squares, and they're increasing. And they have second difference constant and equal to 2. I'll explain what that means in a minute. Then necessarily they have to be consecutive squares. So what is this business of the second difference being equal to 2? Well, you take pairwise. The first difference is you take the sequence of pairwise differences. And then the second difference is you take that sequence and you take its first difference. And that's the second difference. But another way to say it, so this is second difference equal to 2. Another way to say it is that for all n between 1 and m minus 2, Sn plus 2 minus 2 Sn plus minus 2, Sn plus 1 plus Sn is equal to 2. So that's the expression for the second difference. You just work it out, and that's constant equal to 2. Okay? So that is this statement here. Now, it's very easy to see that if the SNs were consecutive perfect squares, this certainly would hold. Okay, the second difference would actually be equal to 2. Just work it out. What Büchi was conjecturing is that it was the converse, yeah. And also Büchi concretely conjectured that m equals 5 would do. Yeah, question? Yeah, I should imagine that I had written this. There is some m such that, yeah, imagine I'd done that. Thank you. Other questions? Yeah.
Is there an example with
Yeah, there are many such examples, and there are infinite families of such examples. I don't remember off the top of my head an example with 4, but there are infinitely many. But certainly one example is if you take, I believe, 0 square, 1 square, and 7 square. So that is obviously 49, that is 1, that is 0. And now you can check that, oops, sorry. 710, yeah, exactly. Sorry, so start over. So I think I have this, yeah. So I have squares, they're not consecutive. But if I take 100 minus 2 times 49, plus 0, indeed this is equal to 2. And you can come up with,
One group is starting with 6 and 23.
Yes, correct, yeah. I don't remember the other one. Obviously, you know, if you Google Büchi, there's a whole Wikipedia entry on this Büchi problem. And there are obviously, there are links and so on. This problem has been extensively studied. And it is also studied by algebraic geometers. It's shown that the Bombieri-Lang conjecture in algebraic geometry implies that there is some value of m for which this is true. And in fact, they show that for m equals 8, there can be only finitely many counterexamples. So if there are only finitely many counterexamples, that means that for a sufficiently large value of m, there are no counterexamples, at which point you have the conjecture. What Büchi conjecture was that m was equal to 5, and this is what has been proven in this unrefereed, unpublished paper, as of yet unpublished paper, by Stanley Zhao. So, Stanley Zhao proved m equals 5 that there are no counterexamples, so that the conjecture is correct. Yeah.
Can you repeat? Did you just say that it's true for m equals to 8, except for finite?
No, sorry. The Bombieri-Lang conjecture says that for m equals 8, there are at most finitely many counterexamples. Yeah. So that implies that if you believe the Bombieri-Lang conjecture, that implies that for a sufficiently large value of m, that depends on the number of finite counterexamples, you need to roll them out one at a time, you're eventually done. Okay, does that make sense? Other questions? There's a survey of this by Barry Mazur, where he sort of explains the attendant algebraic geometry and the various approaches and so on. And this proof of that links to Bombieri-Lang conjecture is actually a result of Vojta from the 1990s. So Paul Vojta is the one who proved this. Okay, so let me now. I'm just going to erase these counterexamples. So in the spirit of trying to restrict this further, so we get decidability, what is the next restriction one might do? So suppose you believe that this is undecidable. Can we somehow further? So we looked at the existential fragment. Is there anything we could do to restrict it further?
So you say that this conjecture implies undecidable.
Correct. Yes. So Büchi, I should. So yeah. So.
Because you've got a formula and you can implement the multiplication.
Yes. So the Büchi conjecture implies undecidability of this fragment.
If you knew the m.
No, even if you don't know the m, because undecidability just means that there has to be some m, because if you had a Turing machine, it would be wrong for whatever value of m is. But anyway, the point is, here we don't even have to worry about this because we've been told m equals 5. The point is that in this proof that I have on the top, the only thing that I was not able to do in the existential fragment is this business of quantifying over the quantifier over that there being no squares between two squares, right? That I need to be able to say they're consecutive. In other words, for all points in between, they're not a square. Okay? But the Büchi conjecture gives you that. Because it tells you, suppose you want, okay, let me just spell it out. Suppose you want to know that u and v are consecutive squares. So what do? You say that I've got u, v, and now I'm going to run out of letters, so I'm going to write v1, v2, v3, v4. And I'm saying that's a square, that's a square, that's a square, that's a square, that's a square. They're all increasing. And moreover, whenever I look at, the second difference of the sequence is constant and equal to 2. So all that just requires existential. There exists u, there exists v1, there exists v2, there exists v3, there exists v4, such that blah, 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 blah. And now I have that, I'm able to extract the square root of u. But by the same trick, the proof then goes the same as above. Does that make sense? Okay, one way in which we might try to circumvent that problem is by restricting the number of free variables you can have. So this is something that's been also extensively studied in logic and in finite model theory, is when you have a logic, but now you restrict the number of variables. So there's the two variable fragment of so I can now either consider the existential fragment of the two variable fragment or not. So this is something where I'm agnostic at this point. So what am I talking about here? The two variable fragment, that's what the two here means. That means that the only variables I have are x and y. I'm not allowed to write any other variable name than x and y. I can reuse these variables, okay? But I'm not allowed to use w or v or something. And now the question is, can I decide that fragment? So that's currently open. I think it's a very difficult question. So, and because this is a research school, I thought I should have some open problems. So, so this is open. I think it'd be a fantastic result. One thing, though, you might say, how strong is this fragment? This fragment, and this was pointed out to me by Mihir, who's a PhD student, this fragment is strong enough to express the Büchi conjecture. And which maybe seems a bit surprising, because I'll just erase this. It looks like the Büchi conjecture requires me to have at least 5 variables. Yeah?
So I can't even solve f of 1.
Yeah, okay, so great. So,
And you can express some non-trivial things like about x times 3 plus 1 squared.
yeah, fantastic. Okay, thank you for the question. So, so that's also open, but I'd like to ask people not to work on it, because we're currently writing a paper on this. So I think this is solved, but so this looks ridiculously simple. I mean, you might say, how can you say anything interesting in this fragment? You've got one variable. How can you say anything interesting? Well, you can talk about generalized Pell equations and simultaneous solution of generalized Pell equations, and the existence or non-existence thereof, which is quite a non-trivial thing. So I'm just since we're on the topic, I will just explain this. Okay, so you have this fragment here. You just have one variable. So what can you say? Well, one thing you can say is that so you can write ax plus b. So here a and b are constant. Like maybe I'll write 3x plus 2. I can write this, and I can say, well, you know what? This is a square. And maybe 7x minus 6, I can say, well, that's also a square. And so saying that it's a square implicitly means, now it's not in my logic, but what does it implicitly mean? It means that there's a u such that u squared is equal to 3x plus 2. This u is not a formal variable. I'm just saying what it means to be a square. So that's what this is saying. And this is saying there's a v such that v squared is equal to 7x minus 6. And so if u squared is equal to 3x plus 2, then of course u squared minus 2 divided by 3 is equal to x. And v squared plus 6 divided by 7 is equal to x. And now I can say, and now of course x is equal to x. So I have that u squared minus 2 times 7 is equal to 3 times v squared plus 6. And so I have here an equation involving two square variables. And I want to know is this solvable. So if I say there exists an x such that this, I'm really saying that there exists u and v such that this holds, u and v integer. Okay, so is this clear? I'm not allowed to write there exists u and v, I don't have u and v, but I'm saying that by writing this, I'm asserting that. But that's a generalized Pell equation. And in fact, you can get essentially arbitrary Pell equation, and you can get simultaneous Pell equation. So what's a simultaneous Pell equation is when you use so you've got some equation in u and v and some equation in w and v, and you want to know can they be simultaneously solved. And you can do this as well, of course. So okay, so this is actually quite powerful. So we think we can do it. I mean, simultaneous Pell equations can be solved. Of course, you can say more in this fragment, but you can at least say that. So this is work in progress. So whoever asked the question, just wait a few months, and hopefully we will produce a decidability result. Okay, does that make sense? Any questions on that? Let me. In the spirit of putting some open problems.
Interrupting, did you solve the full FO1?
Yes. 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 Well, it's not written. Assuming it all works. So you can ask this kind of question, where now you say, I've got a predicate say something is a perfect square, and I've got a predicate for something saying is a perfect cube. Yes. 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 We use, this is one of the tools we use, but the point is, of course, you have to look at the full logic, right? The full logic will have, you start conjoining this with other things and so on and so forth. So you can, yeah, so you also can say something is smaller than something else, you don't just have equations. So you have to be able to handle everything. Well, you can have infinitely many solutions to a Pell equation. And then amongst these infinitely many solutions, then you may make some further assertions about what other properties these solutions may satisfy. You're restricted because you're there, but you're not so restricted. I mean, you can still say things. So I don't think it's an unsolvable problem. Well, we think we can solve it, but it's not completely straightforward. So here is something more complicated, where I'm saying you've got a square predicate and a cube predicate. So you can say something is perfect square, something is a perfect cube. Okay, still just one variable. So what's the obvious thing that comes to mind in terms of the sort of hard things you might be able to talk about? Yes, but it has a name, right? And the number theorists like this very much. What kind of equations involve squares and cubes? Who said that? Fermat, but elliptic curves. Elliptic curves are all about squares and cubes. So here you can essentially define arbitrary elliptic curves and ask not for rational solutions to those, but for integer solutions to elliptic curves, which can be done, but it's a very sophisticated technique to do this. And you can say more. So there's also something we're working on. So maybe, again, hold on a little bit. So what about, yeah, so I'm just going to write down a couple more things, and then perhaps afterwards I'll stop. So what about replacing n by q? So you can ask these questions. Now, Pressburg arithmetic over the rationals is not very difficult, because solving Pressburg arithmetic over the rationals is essentially solving it over the reals, because all the solutions all the sets are going to be rational subsets of real numbers, and you can solve it over the reals. But once you start adding these predicates, all of a sudden, the question becomes completely open when you talk about rationals. I mean, the point being, of course, that over the reals, any positive number is a square. So if you say square, you say a real number is a square, is a perfect square. If it's positive, that's essentially asserting the number is non-negative. Over the rationals, of course, not the case. So one quarter is a perfect square, 1/5 is not. So so these questions all make sense over the rationals. And I'm going to just add a couple more here. So I'm still over the integers now. And I've got squares and cube, but of course, I could ask, I could give you an arbitrary collection of polynomials and say, well, instead of perfect squares and perfect cubes, I give you P1 up to Pk. These are all univariate polynomials, and by writing down P1, I say that P1 of x asserts that x belongs to the set of values that P1 can assume. So if you look at the set P1 of 1, P1 of 2, P1 of 3, P1 of 4, the set of values P1 can assume is x is one of those, right? That's what. So instead of squaring predicate here, I've got an arbitrary polynomial. So this is probably quite difficult. And lastly, how about Büchi's problem for perfect cubes. So Büchi's problem for perfect cubes, you take this formulation and you say, well, let this be a sequence of increasing cubes. And now you want to assert, there is some m, such that whenever you've got a sequence of increasing cubes, if not the second difference, but the third difference is equal to 6, okay, this is what consecutive cubes would suffice. So if the third difference is equal to 6, then the SIs are all necessarily consecutive cubes. The significance of this is that if you add the cubes predicate to Pressburger, if you're able if this conjecture holds, you immediately get decidability of the existential fragment, because in the same way that you can use square to extract square roots, you can use cube to extract cube roots, and you can play essentially the same game. It's a little bit more complicated, but it's just arithmetic and moving things around, and then you get undecidability as well. But this is probably an extremely difficult problem. One interesting question is, would it follow from the Bombieri-Lang conjecture? This is perhaps much more tractable. Let me just check, but I think I will stop here.
Let's first thank the speaker.